Okay, so good evening all. Today I will going to take the last route soldering session of this MM40 aluminum based alloys and metal matrix composite course. So in this lecture we will cover through the all topics covered in studied in this course. So let's start. So the aluminum alloys are known for its high strength to weight ratio, means they have low density and high strength. So the pure aluminum properties we are listed in this slide. So the density of aluminum is generally 2.7 gram per centimeter cube. Hello. Good evening, Monir.
Good evening, madam.
Okay, so can we start today's session?
Yes, ma'am.
Are you able to see my screen?
Yes, ma'am. Visible.
Okay. Okay, so first we start with the introduction of aluminum alloy. So the properties of aluminum alloys are listed in this slide. So the aluminum alloys are known for its high strength to weight ratio. So the um, its density is generally 2.7 gram per cc, melting point 660 degrees Celsius. So the low melting point of aluminum alloy allows it to uh, easy forming processes, means forming processes are easy because of this low temperature, and its boiling point is 2270 degrees Celsius. Thermal conductivity is high. So because of this thermal conductivity, it is usually preferred in preferred in utensil applications. Thermal expansion coefficient is generally 23.5. It's means in moderate range. The electrical resistivity is very low, so it is very high conductivity. And the crystal structure of aluminum is FC, face sintered cubic. So the face sintered cubic crystal structure of metals is very uh, profound, and this crystal structure enables the metals to uh, have the high ductility and strength.
Madam, slide is not changed.
Okay, I'm going to the first slide. Okay, just wait. So now it is changed.
Yes, ma'am.
Okay, so it has the density of 2.7, melting point 660 degrees Celsius. The boiling point is 2270. It has the high thermal conductivity, means we are talking about the pure aluminum properties. And the thermal expansion coefficient of the aluminum is generally 23.5 into 10 raised to power minus 6 per Kelvin. and it has the very low resistivity, means the aluminum has the high conductivity. The it has the crystal structure of FCC. For that, the lattice parameter is 4.05 angstrom. Aluminum has the atomic number of 13 and weight 26.98. It is the paramagnetic material and has the high corrosion resistance. The elastic modulus is around 72 GPa and shear modulus 27 and Poisson's ratio is 0.34. So coming to the impurities in aluminum is what are the sources of impurities in aluminum alloy? So first comes from the extraction process. So from the purities coming from extraction process are alumina, iron, silicon, nitrogen, gallium and phosphorus. And the uh, impurities coming from the makeup chemicals are generally the modifiers, fluxing agents and the alloying elements, or the modifiers to refine the aluminum ore. So the phosphorus, silicon comes from them. The anode carbon can also, anode carbon during the refining process produce the nickel, manganese and iron impurities in the aluminum. And other sources are refractory lining and steel tooling. And the type of impurities are generally the elemental, inclusions and gases. So in elemental, the iron, tin, zinc, copper, magnesium, manganese, titanium and many other elements are present as the impurities in aluminum. Second is the inclusions. So inclusions can be formed because of the reaction between non-metallic elements and metallic elements that form the oxides, nitrides, carbides and boroids, and some intermetallic compounds also. And gases can be the hydrogen gas, means hydrogen gas has the high affinity to dissolve in liquid aluminum. So after the solidification, the hydrogen gas, if it is not able to escape from the liquid metal during solidification, then this create porosity. And the application of pure aluminum is generally in the electrical conductors. So in electrical applications, the 99.5% aluminum EC grade is generally used. So the 1350 is the one of the designation used in electrical conductors. Next is the packaging industries, like we can see the aluminum cans, and containers. Then in chemical industries, in forming different chemicals. Then in household and architecture. So household, we can know the different utensils and appliance bodies. And architecture also in architecture. So the aluminum is used because it provides the good surface finish. And some more application are the car bodies and machine bodies also. So next we will study about the extraction. extraction process of aluminium. So the aluminium is extracted from its alloy, which is generally known as bauxite. So bauxite has two types of mineral. First is gibbsite, which has the formula of Al2O3.3H2O, and diaspore, Al2O3 and H2O. So the gibbsite has the 65.4% alumina in it. Means the percentage of alumina in gibbsite is 65.4, while and in the diaspore the alumina percentage is 85.4%. And impurities in bauxite are generally Fe2O3, means Fe2O3, TiO2 and SiO2. So the extraction process has the two ways. First is the carbothermic reduction and second is electrolytic reduction. So the carbothermic reduction needs a very high temperature up to 2000 degrees Celsius, because the Al2O3 is a stable oxide. So to disintegrate the aluminum oxide needs very high temperature during carbothermic reduction, and that's why it's not preferred. Second is the electrolytic reduction, that works on generally at 220 degrees Celsius. So the electrolytic reduction is generally applied. The electrolytic reduction further has two processes. First is the Bayer's process and second is Hall-Héroult process. So we will study the Bayer process method. So in the Bayer process, first the bauxite ore is fed to the crushing, grinding and classification up to the 100 mesh to reduce the ore size. Means then that crushed and classified ore material is fed to the leaching chamber, in which steam is provided. Then the product obtained from the leaching is gone through the settling. So in settling process, the starch is added into the feed. So after the settling, the washing of the ore is done. So after washing, the filtration of the ore particles are done, in which a liquor is obtained with red mud cakes. So red mud cakes are the secondary product and are not in use. So the liquor is further fed to the heat exchanger. So in heat exchanger, the hot liquor is cooled to a lower temperature. Then that cooled liquor is fed to the precipitation. So precipitation processing. So after the precipitation, the slurry is obtained. So that slurry is fed to thickening process. So in which thickening process, the Al2O3 hydrate is obtained. And then that Al2O3 hydrate has the is fed to the rotatory kiln to form the anhydrous alumina. And this anhydrous alumina will further fed to the Hall-Héroult process, in which the cryolite we know as cryolite, that is known for the that is used for the dissociation of Al2O3. So in the Hall Herald process, the cryolite is added, which has the composition of Na3Al(F6). So this reagent reduce the temperature to dissociate the alumina, and by reacting and forming the different byproducts. Then next, that so the aluminium obtained from the Hall Herald process is further refined by different process. First is the fluxing. So fluxing is done to remove impurities. So in fluxing, generally NaCl and KCl is mixed with the liquid aluminium. So this NaCl and KCl interact react with the impurities, like impurities we studied, like different elemental iron, silicon. So these two flux react with the elemental and oxide properties in the liquid aluminium and remove them as a as a form of slag. Then degassing is done to remove the hydrogen gas. So the gas degassing is generally done by vacuum, argon gas purging, and the adding of the C2Cl6 tablets. So the C2Cl6 tablets are also known as blue tablets. So that react with the gases present in the liquid metal and remove, and therefore able to remove the impurities and the gases from the liquid metal. Then filtration is done to remove inclusions and solid impurities. So for the filtration, the porous refractory material is used. And filters, other filters can have the fiberglass, tabular alumina filter, and ceramic foam. So these are the different filters used for in the filtration process. Next is the different aluminium grades. So the high purity aluminium generally has the 99.8 to 99.949% of aluminium. Then super purity aluminium alloy has the 99.95% to 99.9959%. Then the alloy which has the more aluminium content is called as the extreme purity aluminium, which has the concentration from the 99.996 to 99.999. Then the ultra purity aluminium has the aluminium content greater than 99.999%. So beside these pure aluminium grades, the aluminium alloys which are generally used are divided into 8 categories. So the aluminium alloys can be divided, that are classified as a different series, which is known as the 1x, 2x, 3x, 4x, 5x, 6s and 7x and 8x. It can be written as the 1000 series also, 1000, 2000. So the 1000 series is pure aluminium. So that the properties of pure aluminium is the strain hardenable, except it has the exceptional formability, means easy to process and forming complex shapes. It has the high corrosion resistance, high and high electrical conductivity. Second, the 2000 series alloy, which has the copper in it, means the major alloying element is the copper in 2000 series. So it is heat treatable, means the strength can be generate strength can be increased via any suitable heat treatment. Then it has the high strength, low corrosion resistance, and generally used in aerospace manufacturing. Next is the 3000 series alloy, which has the major alloying element as manganese. So manganese provide the highly provide means because of the manganese, the 3000 series alloy is the highly formable. It has the corrosion resistance high and medium strength. It is strain hardenable, and the application are in beverage cans and tubing. And the next are the 4000 series alloy, which is aluminum silicon alloy. So the aluminum silicon alloy has the properties it is some of them are heat treatable, but some of them are not non-heat treatable. It has the good flowability and weldability. So the good flowability and weldability comes from the silicon present in it. Then it has the medium strength, and application are in automotive use and filler materials. Filler materials means the welding and brazing application. Next are the 5000 series alloy, which are the aluminum magnesium alloys. So these alloys are the strain hardenable, excellent corrosion resistance, toughness, high toughness, good weldability, moderate strength, generally used in building, construction, automotive, cryogenic and marine applications. The 6000 series alloy, which has the major alloying element as magnesium and silicon. So these alloys are heat treatable, has high corrosion resistance, moderate strength, readily welded by gas metal arc welding and gas tungsten arc welding. And the 6000 series alloys also has outstanding extrudability. So that is very useful for automotive parts and different different shapes can be formed from the 6000 series alloy. And the 7000 series alloy which has the major alloying element as zinc, this is heat treatable, has very high strength, special toughness, and special toughness versions are also available in the 7000 series alloy and generally used in aerospace and automotive. The 8000 series alloy, which are the aluminum lithium, it is the also heat treatable, high conductivity, strength means high strength, high hardness, and generally used in aerospace applications. So in the aluminum alloys, the 2000 2000 and 6000, 7000 and 8000 are the heat treatable alloys, while other the 1x, 1000, 2000 3 no 2 3000 4 and 5000 series alloy are wrought alloys, means the strength is increased by strain deforming process. So what are the mechanism by which these alloying elements are able to increase the strength and toughness of these of the aluminium? So the strengthening mechanism related with the aluminium alloys are the solid solution strengthening, dynamic strain aging, precipitation hardening, and strain hardening mechanism. So in solid solution strengthening, the alloying elements which has the, like, first if we consider the aluminium, magnesium or copper alloy, so the atoms of alloying element magnesium and copper has the different elastic modulus, difference in elastic modulus, different radius, atomic radius is different. Then the electronegativities of these element as compared to aluminium is different, and valencies also different from the aluminium. So because of the difference in elastic modulus, its radius, electronegativity and valency, the different interaction generates, and that lead to the strength, means because of this interaction strain field creates around the inside the material, so that increase in strain field increases the stress provided for the further deformation process, so that lead to the solid solution strengthening. So in which the elastic interaction comes, modulus interaction comes, stacking fault interaction, means stacking fault, so the dislocation generally dissociates into stacking fault and stacking faults. So the energy associated with stacking faults lead to strengthening in the alloy. And next is the dislocation interaction, means the alloying elements can also interact with the dislocations, means the small alloying element can prefer to sit above the dislocation, and the big alloying elements which has the high radius than the aluminium are preferred to sit at the bottom of the dislocation core. So this during the movement of dislocation, the alloying elements hinder the path of dislocation. So due to hindering, the stress stress required for further deformation will increase, so that lead to the yield point phenomena. Means during yield point phenomena generally happens, means if the alloy strain is deformed to a certain point and reloaded, and if it and unloaded, and if it is reloaded after some time, the yield point will increase. So the increase in yield point corresponds to the more in the means locking of dislocation with these alloying elements. Again, means the atoms lock the dislocation again. Next strengthening mechanism is the dynamic strain aging. So the dynamic strain aging happens because during the change in strain rate, means with increasing strain rate the material the material require less stress for the further deformation to happen. Why the dynamic strain aging happens? Because as the strain rate increase, the time for locking of dislocation, means the alloying element could not cannot get the time to lock the dislocation path, and the stress value decreases for further deformation. So means the dynamic strain aging is related to the strain rate sensitivity. Of the alloys. So with increasing strain rate, the stress required for the deformation reduces. And next is the precipitation age hardening process. So the precipitation age hardening generally happens in the 2000 and 7000 series alloys. So and 6000 also. So in these alloys, the alloying elements form intermetallic compounds with aging, with time after the after the alloy formed or subjected to any deformation. So with time, the intermetallic particles form and grow. So hardness is generally measured during the aging process, and it is also the hardness will, so the strength can be correlated with the hardness. So with time the hardness increases and reaches a maximum hardness for a particular time and for a particular particle size. So this is peak aged condition, and this is overaged. Means with time the particle size increased to that level, so that makes the stable intermetallic compound, so that due to the increase in particle size the hardness decreases of the hardness of the alloy decreases. So the in the precipitation hardening also different mechanism of strengthening happens, because the interaction between intermetallic particles and the aluminum solid solution matrix. So first is the stacking fault energy interaction, means the stacking fault energy between the intermetallic particle and aluminum matrix result in the strengthening. Then order structure hardening, means the intermetallic particle can have some ordered structure. So due to the ordering difference between the intermetallic and the aluminum matrix result in the hardening. Then modulus effect, means the intermetallic modulus will be different from the aluminum matrix. Then the interfacial energy, means in the particle when the dislocation move, that movement of dislocation generates antiphase boundaries. So the energy of antiphase boundaries also lead to strengthening in the precipitation hardening alloys. Next is the lattice friction, means how much lattice friction the particle is experiencing uh, during the deformation process. And next is the strain hardening, means strain hardening generally occur with the deformation process, means due to deformation the dislocation density increases. So the increase in dislocation density increases the strength of the alloy. So these four are the strengthening mechanism in aluminum alloys. Next is the, so after the strengthening and deforming process, the annealing process comes in the picture to recover the previous microstructure or to refine the microstructure further. So the annealing process has three steps. First is the recovery, second is recrystallization, third is grain growth. So the recovery is done to annihilate the point defects and formation of low angle grain boundaries by rearrangement of dislocation. Monir, you can ask in between also if you have any doubt.
Yes, ma'am.
Rearrangement of dislocations that lead to formation of low angle grain boundaries and polygonization, and the increment in electrical conductivity, means as the point defect decreases, the electrical conductivity of the alloy will increase. Next is the recrystallization process, in which the nucleation and growth of strain free grains generally observed. And during the grain growth, some grains which are favorable, which has the favorable orientation, grow at the expense of small grains which has the which does not have the favorable orientation. So this is the annealing process and the three process. So the this recrystallization is happening during the heat treatment process. But the recrystallization can also happen during the deformation process when temperature is also high. So the recrystallization happening during the deformation is known as the dynamic recrystallization. So the dynamic recrystallization occurs during deformation when heat and stress are both simultaneously applied. That process is known as the thermomechanical process. An example can be given as hot rolling, extrusion, or any deforming process at high temperature. So the dynamic recrystallization is also can also classified into three different types depending on the formation of new grains. So first is the discontinuous dynamic recrystallization, second is continuous dynamic recrystallization, and third is the geometric recrystallization. And next is the grain refinement method, means during the recrystallization process what mechanism, means what phenomena occur during the recrystallization process that lead to the grain refinement, means the recrystallization also generates finer grains. So the finer grain so due to the fine grains, this will lead to grain size strengthening or grain boundary strengthening. Which is given by Hall pitch relation. The Hall pitch relation is generally written as sigma equals to sigma naught plus k divided by square root of d. So here sigma naught is the lattice frictional stress when no defect is present. K is the locking parameter, and D is grain size. So as the grain size decreases, the grain boundary area will increase. Means as D is grain size decreases, the grain boundary area will increase. So due to the increase in this area, the dislocation will feel more restricted, and that lead to the increase in stress. Means is or so the strength of the alloy will increase. So there are other methods also for grain refinement. Means apart from the deforming process and annealing process, the different grain refinement methods can be generally during the first grain refinement is during the melting and casting. Means apart from the deformation and annealing process, before the deformation, during the processing method, the grain can be refined. Grain refinement can also be done during the manufacturing process. So first is the during melting and casting. So the solidification behavior of material is modified in a manner that lead to fine grain size. So during the melting and casting, the liquid metal will solidify, and the grains grain nucleation occur in the liquid metal. So the nucleation of grains can be classified as two types. Means first is the homogeneous and second is heterogeneous. Means homogeneous nucleation occurs without any add of surface throughout the solidifying liquid metal, while the heterogeneous nucleation occur on a surface as defects, mold walls and second phase particles. Means the nucleation process generally requires the two types of energies. First is the as the nucleus form, that requires the volume free energy, delta GV, and the surface created of this nucleus will lead to surface energy. So the general formula of total energy can be written as 4 by 3 pi r cube plus delta GV plus 4 pi r square into gamma. This is surface energy. So the relation between these two energies with the radius of nucleus result in the uh, free total free energy that leads to the uh, nucleation and decides the whether the nucleus will grow or dissolve in the liquid metal again. So the curve formed during the nucleation process. So this curve is for the surface energy gamma, and this is for volume free energy. So the resultant curve will follow this path, means after a certain radius of nucleus the energy of the nucleus will decrease, and as the energy decreases the nucleus will become stable. So that's why means in this way the nucleation process uh, proceeds. So the homogeneous nucleation is very difficult because it has no any no surface to for the nucleation. So in heterogeneous nucleation, the interfacial energy associated with the nucleus and the second phase is, so the relation between interfacial energies lead to the less energy required for nucleation. So the delta G star for this heterogeneous nucleation is very less than as compared to a homogeneous means energy barrier for homogeneous nucleation. So due to the low energy, the means low energy barrier, the nucleation rate will be high, that lead to green refinement. And generally the heterogeneous nucleation is more prevalent in practical scenarios because any other type of the mold wall is generally already present for the nucleation, and some impurities are always present in the liquid metal. That lead to heterogeneous nucleation. Next method of green refinement is the melt inoculation. So what is melt inoculation? Means some type of elements which does not dissolve in the liquid metal is mixed into the aluminium, liquid aluminium, and the grain refining element are generally the titanium, boron, zirconium, tantalum, tungsten, vanadium, and niobium. So these are the different grain refining elements, and all these elements has high melting temperature. That's why they are used as inoculation as inoculant in the during the solidification process. So these elements either act as secondary particles or form intermetallics in the melt. So that intermetallic also provide the surface and lead to the heterogeneous nucleation. So that heterogeneous nucleation result into the different types of theories. Means one is the carbide theory, carbide and boroid theory. Means the carbide can form as titanium carbide, titanium diboride, So the energy associated with the titanium carbide and titanium boride means the uh, just 1 second. Yeah, means the boroid which forms during the uh, reaction or means the different carbide and boroid has different interfacial energies, means due to the interfacial energy they will provide the nucleation surface more efficiently or less efficiently. Means the as we see, the titanium boroid has the uh, uh, means does not provide efficient nucleation surface because it has the high disk registry with the aluminium nucleus that will nucleate on the its surface. Means the as we can see the incoherent or coherent boundaries. So the titanium boride has incoherent with aluminium nucleus. So this formation of this boroid will not prefer, while the titanium carbide has the low disk registry and helps in the in generation of more nucleation, more nucleus. So this leads to high nucleation rate and more grain refinement. In peritectic theory, the Al3Ti intermetallic wedge formed during the uh, inoculation process uh, forms the aluminium aluminium nucleus before reaching the solvus temperature. Means from the Al3Ti plus liquid provides the alpha aluminium nucleus at 665 degrees Celsius, and the solidification temperature of aluminium is 660. So this reaction happens before the solvus temperature reach. So this is how this contributes in the nucleation process. Next is the peritectic hull theory. Means the this Al3Ti particle intermetallic can also dissolve during the solidification process. So the this dissolve the so the dissolution of the particle lead to further means lead to further uh, reaction with the other elements present in the liquid metal, so that lead to strain hardening, means grain refinement method. Next is the hypernucleation theory, in which the liquid Al3, means the uh, remelted Al3Ti particle will be surrounded by different elements, means if this is Al3Ti intermetallic and this is means titanium particle, so this will be surrounded by different types of aluminum atoms. Then above that, so due to this these aluminum atoms are fixed to this dissolving Al3I intermetallic, and upon that the some aluminum atoms will be there, so that so the aluminum atoms above this first element, above this first aluminum atoms are restricted, means the mobility of these elements are restricted due to this cluster formed, so the mobility will of this particle will be less. So this is how, and further particles, further atoms will attach to this cluster and lead to the hypernucleation of some other uh, compound. So this also lead to the uh, grain refinement. So this comes under the hypernucleation theory. Next is the fading or poisoning theory, means grain refinement efficiency decreases and lost with time, as the means with the addition of these alloying grain refining elements. First the nucleation rate will be high, but as the time proceeds the nucleation rate will decrease because of the forming of different clusters and remelting of the intermetallics, or the settling of these intermetallics or grain refining elements, that lead to the fading of the grain refinement efficiency. Poisoning is the means the if zirconium is present, that lead to means that prevent the grain refinement, when that does not help in the heterogeneous nucleation, means if if zirconium is present, that will stop the Al3I and means the hinder the grain refinement occurring due to intermetallic, and thereby reduce the grain refinement efficiency. In the solute theory, the means the if the solute segregation of solute is happens during the inoculation process, so the segregation also lead to the less grain refinement. And the next is the particle settling theory, so in which the or I will explain in the other slide. News means in the particle settling theory, a curve is of the grain size is obtained, grain size versus holding time. So the grain size decreases with holding time for a certain period of time, and grain size will start to increase after some time. So the this part of the curve is related to the fading effect. Again, if some recovery of grain refinement is occurred because of some agitation process, then again the grain size will start to decrease and it will start to again increase, means there will be no decrease in grain size. Because so this is the critical time when the grain size first start to, means the grain refinement first starts to first stops, and this is at the time of stirring, so the grain size increases. So this part is can be written as the recovery of grain refinement. So the TC can also be referred as contact time, uh, or time elapsed. Um, Between addition of master alloy and casting. And the grain size associated with this TC time is generally known as the ultimate grain size, UGC. So the UGS means ultimate grain size. Means this is the optimum grain size that can be achieved without any particle settling. So these are the different mechanism related to the melt inoculation. Next is the mechanical or electromagnetic stirring. So in which the mechanical stirring also the different mechanism occur. So first is the shear mechanism of dendritic arm. So shear fracture mechanism means the dendritic arms can during the solidification can break due to the shear force experienced because between the liquid metal and the dendritic arms, liquid, and this is dendritic arm. So because of this shear force present, the dendritic arm will fracture, and the broken dendritic arms lead to the means the broken dendrite arms provide the more heterogeneous nucleation sites and increase the grain refinement level. Second is the grain boundary infiltration, in which the low angle grain boundaries transforms into high angle grain boundary. By plastic bending mechanism, means plastic bending of dendritic arms. So the orientation of grain boundaries will change because of this plastic bending and lead to the formation of high angle grain boundaries. So that the formation of high angle grain boundaries increases means the increases the solid liquid interface energy and detached due to the increase in solid liquid interface energy. The dendrite arms break, and the same mechanism will happen because of the in the first mechanism means the broken dendritic arms lead to higher heterogeneous nucleation. Then remelting of dendritic root can happen because of the stress associated around the root of dendritic arm. Then crystal rain is happens as the um, as we know that the nucleation rate is high at the at the mold wall, and when the mechanical stirring is applied in the melt, so the uh, crystal nucleus formed around the mold wall will detach from the mold wall and dispersed in the liquid. So the due to the increase in nucleation particles in the liquid metal, the crystal rain means the nucleus will fall in the liquid and leading to the uh, increase in heterogeneous nucleation. Next is the ultrasonic cavitation. So the in the ultrasonic cavitation, the the due to the means the melt is subjected to ultrasonic sound, and that ultrasonic sound lead to the porosity means pores agglomeration and burst that form a cavity type, and as the cavity of these agglomerated pores burst, that lead to a localized high pressure. So this localized high pressure lead to the supercooling of the liquid, and the supercooling will further lead to heterogeneous nucleation. Next is the electromagnetic convection, in which the electromagnetic field is applied in the liquid metal, so that will affect the nucleation process same as the mechanical stirring process. And last is the severe plastic deformation. So due to the severe plastic deformation, the dynamic recrystallization generates in the liquid metal. No, this is severe plastic deformation will be in the solidified metal. So that will lead to dynamic recrystallization, and we studied that the dynamic recrystallization generally leads to finer grain. and the process associated with the mm, severe plastic deformation are the high pressure torsion, means the severe SPD process can happens in the high pressure torsion process. Second is the equichannel angular pressing. Cyclic extrusion. Compression. Continuous cycling. Cyclic bending. Cyclic bending and repetitive corrugation and straightening. Some more are the accumulative roll bonding, and seventh is friction stir processing. So the severe plastic deformation can be generated in the aluminum alloys by these processes. So in these processes, the component is subjected to different deformation process and deformation stages that lead to a generation of preferred structure. Preferred texture in the grains and increases the dislocation density. And the high number of high angle grain boundaries will increase. So this all lead to fine grain structure. Next so this is the all grain refinement mechanism or grain refinement method in the aluminum alloys. Next we will study the aluminum based metal matrix composites. So the aluminum based metal matrix composites are formed to associate the ductility of the aluminum matrix with high strength of reinforcement. Reinforcement phase. So the metal matrix composites have the high specific strength, high modulus, low thermal expansion coefficient, and high wear resistance. And also the corrosion resistance of the aluminum based metal matrix composite is also high. So the processes related to the formation of the metal matrix composites are divided into two parts. One is the three parts: liquid, solid, and vapor state. So the in the liquid state processing method, first is the stir casting, second melt infiltration, and third is the spray deposition. In solid state process, first is the powder metallurgy, second is diffusion bonding, and the third is high energy high rate process. And third is the vapor state process. So in the vapor state process, the chemical vapor deposition, physical vapor deposition, and the electron beam physical vapor deposition comes. Means the composites can be prepared by these liquid, solid, and vapor state processes. Next is the means the so in the processing of the the composite, first the how the reinforcement leads to strengthening of metal matrix. So first is the uh, the sorry means strengthen metal matrix by grain refinement also. Means first is the theory that the the when the composite is subjected to a force, means so the reinforcement will means the crack present in the reinforcement is stopped by the ductile matrix, but the grain refinement occurring in the metal matrix uh, due to the presence of composite is is due to first the weighting of reinforcement particles. Means the contact angle between the reinforcement particle and the liquid matrix should be less. Means as the contact angle will be less, so the energy associated with the nucleation of grains will decrease. Means the energy barrier will be low if contact angle is low. Energy barrier is low, then it will lead to more nucleation and grain refinement. So the surface energy of the reinforcement particle and metal matrix should be less. Next is the interaction between solidification front and the reinforcement particle. So the grain refinement due to the addition of the reinforcement particle, uh, it also depends on the in the progression of solidification front when with the reinforcement particle. So the solidification front, if the this also related to the thermal conductivity of matrix particles. Means alpha is a coefficient which is the ratio of the particle thermal conductivity and the matrix thermal conductivity. So when if the particle, so if this ratio is less than 1, greater than 1 or equal to 1, so that will lead to different scenarios. Means when the alpha is greater than 1, means the thermal conductivity of particle is greater than 1, means the Kp is greater than Km. So due to this effect, the reinforcement particles will be engulfed in the metal matrix. this is conducive environment for the strengthening. And if the alpha is less than 1, means the thermal conductivity of reinforcement particle is less than the thermal conductivity of metal matrix. So this lead to the uh, means the solidification front will push the uh, reinforcement particles. Means the interaction between the metal matrix and these reinforcement particle will be less, and that lead to the clustering or segregation. Along interdendritic region. This will lead to less strengthening. Now how the elastic modulus increase in the composite. So the increase in elastic modulus is given by the rule of mixture. Means in the rule of mixture, the elastic modulus also change with the change of loading direction. Change of loading direction. This is means modulus of the composite change with the change of loading direction corresponding to the reinforcement fibers. So if the load is applied in the same direction in which the fibers are aligned, means this is called as the isostrain condition. Means in this the strain in the composite, strain in the matrix, and strain in the fibers will be equal. So this will lead to the elastic modulus of composite, that can be written as the EF VF plus EM into nu m. So here EF is the modulus of fiber and nu f is the volume fraction of the fibers. Similarly for the EM and nu m will be the modulus and fraction of matrix. So the volume fraction, addition of these two volume fraction will be 1. So this can also be written as the in terms of the volume fraction of fiber. So related to the different conditions, the amount for means the volume fraction of reinforcement can be decided to generate a required strength. Means by applying different processes, means during the deformation, the critical fraction of fiber for strengthening can be obtained. So the generally critical fraction of fiber is written as sigma mu minus sigma m dash divided sigma fu minus the sigma m dash. So sigma m dash is the strain is the flow stress of matrix. At a strain corresponding to fracture stress of fiber. This is the fracture stress. Sigma fu is the fracture stress of fiber. Sigma mu is the yield strength of the matrix. Next are the strengthening mechanisms in the composite. So first, is the shear lag theory. Second, dislocation mechanism. Third is grain size strengthening. And fourth is the bulk hardening. And fifth is the coefficient of thermal expansion theory. Mismatch. So so the shear lag theory depends on the fiber length in the discontinuous fibers. So means this tells the fiber length should be high enough high enough for proper uh, load transfer between the matrix and the fiber. So generally the discontinuous fibers provide less strength as compared to uh, long fibers. While in dislocation mechanism, the Oro1 looping Oro1 looping happens, means if this dislocation mechanism, this can be due to particle or fiber also, means if these are the two fiber cross section, or if we consider the reinforcement particle, so the dislocation bow around these particles, and due to the due to this increase in bow, that lead to Oro1 looping when the dislocation leaves the reinforcement, and this further looping will act as the dislocation generating source, and that's why therefore leading to the strengthening in the metal matrix composite. Grain size strengthening happens same as the hole pitch relation, means during the solid state processing, recrystallization happen, that lead to, and this recrystallization is due to the particle stimulated nucleation, means the nucleation happening due to the reinforcement particle. So this lead to the grain size strengthening, means grain size will be low and strength will be high of composite. In work hardening, the plastic deformation, due to the plastic deformation, the means hindrance of the matrix flow is restricted due to the presence of reinforcement, lead to the more strengthening, means the matrix flow is restricted by reinforcement, during deformation process, that leading to work hardening. Next is the coefficient of thermal expansion mismatch, means the mismatch in thermal expansion lead to formation of dislocation, when the strain will be different, and this lead to dislocation generation. leading to the increase in strength of metal matrix composite. And the next is the fracture in the fracture mechanism in the metal matrix composite is described as the first, means the uh, load transfer can occur by d one by interfacial interaction between the matrix and reinforcement. And the load can be released by debonding, means during the deformation process the crack propagation can be uh, crack propagation can be stopped by the due to the debonding of the reinforcement and the matrix. So the interfacial bonding depends on the, means relate to the fracture mechanism in the metal matrix, means as the cracks are small, means is the if interfacial bonding is less, so that lead to debonding. And if it is strong, then the large cracks will grow, and the growth will also be planar. So Moni, do you have any doubt?
No, madam.
Okay, so can we end the lecture?
Yes, ma'am.
Okay, thank you. Or do you have any doubt, you can post in the discussion forum also.
ओके मैडम, और
I will,
मैडम ये पीपीटी आप सेंड कर सकते हो?
हाँ हाँ, मैं आई विल शेयर दिस.
ओके मैडम, थैंक यू.